Morikawa, and this is the 20th episode for VEX for algorithmic design. And the topic for today is about solver basics. And here is the list of topics that I would like to talk today. So starting from basic translation, using solver and basic growth, vector flow on an object, vector flow inside volume, and also polygon modification, basic fractal, and last chained solver. In this session, I'm mostly going to talk about how you can use the solver with exercises, considering the situations you can use solver for. So let me first go through what is solver. A solver is, in general, is a mathematical software which can solve a mathematical problem. But in Houdini, it's mostly used for the frame-based feedback processing system. For example, there are a bunch of solvers available for DOPS, which is for the dynamics, such as fluid solver or rigid body solver and so on. Now what I'm mostly going to talk about is about a SOP solver, a feedback processing system which you can use under a SOP, meaning you can use it for general geometrical modifications based on a frame for the feedback. And this is how it works. First of all, you need a SOP solver node, which you can use it to create a feedback processing system as a network. And this is how it looks like in solver network. First of all, you have an input, then you process this input, then you get the result out of this process. Now it's pretty similar to the normal network, but the difference is that you can loop, redo the process again and again based on the frame. Now let's say this is calculated in first frame. Now after you got the result on the first frame, you can go to the next frame by going back to the input and use the result as the new input in the next frame and use it to do a same process and get the new result, and do this back again on the next frame and continue until the frame stops. So the benefit of using a solver is that you can use the updated result for a new calculation over and over again based on the time, which means you can easily create a growth-like system using this solver. That's what I mean by feedback loop. If you use a for each loop node in Houdini, you can do the similar things in one frame. But if you want to create an animation based on this loop, then using a solver is a way to go. And the benefit of using solver to create your own system instead of using like DOP network is the flexibility of the result you can create. And combining this solver system together with the VEX coding, you can almost do anything. Even you can try to mimic the dynamics in using the SOP solver, if you know the algorithm. So now we understand the basics idea of how SOP solver works. Let's try to do several exercises to use this SOP solver together with the VEX for several purposes so that you'll be comfortable enough to create your own solver afterwards. Okay, so the first exercise that I'm going to show you is to create a basic translation using a SOP solver, which is going to be the most basics way to use the solver. What I'm going to try to do is to try to move the point based on a translation vector for each frame as an animation. Okay, so let's try to do that. I'm going to first create a geometry node, and inside I'm going to create a circle. Let's change this orientation to ZX plane, then create a scatter of points on top of this surface, on top of this circle. Okay, and let's reduce the number of points to something like 50. Now I am going to create a solver. So search for solver, which looks like a brain icon here, and connect the scatter node to the first input. Now first thing you need to remember is that the object or values connected to the first input will going to be used for the initial value inside the SOP solver as an input. For the second, third, and fourth input, you can use them for the guide, and I'm gonna show you within other examples how you can use them. Now, after you have connected the object to a first input, you can double click the solver to go inside into this solver network. Now in total you have 5 nodes available inside the network, and the node which says prep frame is the one that you get the value from the first input as an initial value. And after the first input, the result that has been calculated inside this network is going to be feedback into the prep frame on the next frame. And for all these 4 nodes, these are the reference geometry which you can get from all these 4 inputs. You can also get the reference geometry for the first input right here. The difference between the input 1 and the prep frame is that the prep frame is always going to be updated using the solver, but the input 1 is always the geometry that you get out of the one that you connected to the first input. So, which is not affected by the result of the SOP solver, which sometimes is useful. So remember what it does, what's the difference between these are. Now let's try to move all these points using a SOP solver as an animation. Okay, so what I'm going to do is to first try to create a point wrangle connected to the previous frame node. Let's name this move. And what I'm going to write is a very simple code here. I'm just going to increment the y value for the position by, let's say, +1 plus equal to 0.1. So that has just moved each of the all the points by 0.1 upward to the y direction. Currently it just shows one movement steps from prep frame to a move. Now after you have moved it, this result, the movement is the result that you got here is going to be the result of this SOP solver. If you have this blue flag here, display flag here, this is going to be the last node that's going to be run inside the network. And on the next frame, this final result of this process that you have right here, in this case a movement to the upward direction, will going to be used for the prep frame in the next frame. So in the next frame, this will be the initial position, and by using the same code here, you can bring all those points upward again by 0.1. And by continuing doing this, you'll be able to create a animation based on the frame. Okay, so now let's try to check this animation. You cannot check the animation inside the network. It just doesn't do anything, so you need to go back upward. You go to the parent node, then click Display Animation. And now you can see that the point is animating. Each of the point is going upward by the same speed. So each frame, the point is moved upward by 0.1 using the last point position. So the basic idea of the solver is just like this. It's pretty simple, but there's many ways you can use it for, which makes it really powerful. Now that I have just moved the point upward using a SOP solver, let's try to add another transformation as a practice. So I am going to create another SOP solver. Let's connect to the same points, go inside the network, and I am going to connect another point wrangle. Let's name this move and rotate. So first of all, I am going to I'm going to move this point upward again by 0.1. And as soon as you write something, you notice that the timeline gets orange from blue, which means something has changed during the frame, and in order to have this update being used, you have to reset this timeline. You have to reset the cache of this solver. In order to do that, you can go back to the geometry node and then go to the first frame, and it will reset the cache of the solver. Or you can also press this button, Reset Simulations, to remove the cache. Now you'll be able to do the same things again. Okay, now what I'm going to do now is to add a rotational transformation addition to this one using a matrix, rotational matrix. So first I'm going to create a matrix mat starting with a identity matrix. Then use the rotate function to create the rotation matrix. Let's try to rotate by an angle of 3 degrees for each frame using 0, 1, 0, a y-axis for the translation axis. Now I am going to multiply this rotational matrix to the point position so that the point will be rotated using the center of the system or space as the rotation pivot. Okay, now by just rotating 3 degrees in one frame you cannot really see the difference, but by having it as an animation, you can see that the whole point is rotating like this. Now if you want to see the trail, how this point being moved, you can also use a node like a trail node. And let's connect this and set a trail length, something like 20, and then change the types to connect as polygon. And let's uncheck this closed rows so that it will be created as a polyline. So let's see how this works. Okay, so it shows how the point has been moved using the trail line. Now that we have just done the basic translation of the point using Solver, for our next exercise, let's try to create a basic growth using Solver. Specifically, we're going to create a trail itself inside a solver without using a trail node, which sounds simple, but it's going to be the really important foundation for a growth using Solver. Okay, so first of all, I'm going to create a single line or single point like this. And I am going to attach a group to this point. And I am going to name this as a move. Okay, and I'm also going to create a point wrangle to create a polyline attached to this point. Or just the empty polyline at this moment. So I'm gonna name this create line and say int prim is equal to add prim 0 poly. At this moment, I have just created the empty polyline primitive and no points being attached to this primitive yet. But we're gonna do this interactively or iteratively inside the solver. Okay, now we are going to create a solver like this. Then let's go inside. Now the reason why I have used the point group is that I only want to apply the coding or process inside the solver using this move group filter. So I'm going to create another move wrangle or point wrangle, and let's call this move, and I only want to run this process for the point which have this move group. Okay, and for the move group, I'm iteratively going to move this point like we did last time. So what I'm gonna do, I'm going to first move this point position maybe just Y position, Y.1, and then create a rotation matrix, just like we did last time. Rotate the matrix by, say, 15 degrees, and using Y up direction as a rotation axis, and rotate the point. We're using this matrix. Now let's try to see if this point moves with these code first. So if I play it, okay, I forgot to make this group for the points, so I have to make this points. Then let's do this again. If I move this, you can see that the point is moving upward. It's a bit hard to see if it's rotating or not, so let's try to change how much it goes up. So let's say 0.01 to the Y direction. And also maybe I also need to change the starting point of the point position, because if it's on 0, 0, 0, then even if it rotates, then it doesn't really change the position on XZ plane. So I'm gonna move the point to X by 1, and then let's see how it goes. Okay, now we see the points being spirally moving. Now what I want to do now is to create a trail using this point position. But the one that I only want the point that I want to move is only this single point. And the trail, by creating a trail, you're going to create additional points, but for those additional points, I don't want to move them. So what I'm gonna do is to not attach any move group. Since it's a solver, this move component or move point wrangle only works for the point which has this move group. So even if you add a new points for the trail, if it doesn't have any move group, then it's not being activated, or it's not being affected by this code. So that's the way to go. So in order to create the trail, what we can do is to create a new point before moving the point using the current point. Okay, so before moving the point, the current point will be baked as a freezed point, which doesn't move anymore, and use add vertex to add this point inside the primitive that we have created. And there's only one primitive in this node, so you can say 0, which is the index of the primitive, and MPT is the point number that I have just created. Okay, by doing this, you'll be able to create a trail like this. Now the last point is not connected to the polyline, so there's a little gap here. But you can see that the primitive, or you can see that the trail has been created just inside the solver, and there's no duplicated points. So that's the way to go to create a basic growth or basic trail using solver. So in this exercise, the essential things here that I wanted to show is to use the group node to group the points or primitive that you want to control inside the SOP solver, and for the other part, just keep the geometry as it is, which as a result, for example, you could create a trail like these as a static geometry. Now for the next exercise, I would like to show you how you can create an animated vector field or vector flow to a guided object. The purpose of this exercise is to understand how you can use the guide object for the SOP solver. Specifically, I'm going to talk about how you can use this additional inputs for the SOP solver. Okay, now I'm going to first create a guide object which is going to be a pick head. Could be anything. Okay. Now, what I'm going to do now is to create a vector field on top of this geometry, this pick head, and use it as a guide to move the point. So first of all, I'm going to create a animated vector field using a time-based noise function. Then I'm going to use that as a guide to actually move the point based on those direction of the vectors. Okay, so I'm going to first create a point wrangle to create a vector field in each point of this pick head. So let me show the wireframe. So for each of the point on this surface, I'm going to try to create some vector direction based on the noise function. Okay, so I'm going to create, and I'm going to name this field, and then let's first create a seed value for the noise, which I am going to name this pause, derived from the point position for each point, and multiply by some scale value. For the noise explanation, I've done that in the last episodes so if you're interested in detail how the noise works, you can watch the previous video. Okay. Now let's change the scale to some value. It could be any value here. Maybe I can set the range for this noise scale to something in between 0 to 5. Okay. Let's keep this for around 1.5, and then let's create the direction value using a noise value. Now, what I want to use now is a one called curl noise 2D. The reason why I'm using noise 2D here is because the surface, if you unflatten it, or if you flatten this surface into a plane, it's just a planar surface. So what I want to do and what I want to create is like the vector field which lays on top of each surface based on its normal direction, okay, or tangent direction. So first of all, I'm going to create a 2D vectors, and I'm going to orient these vectors into a surface based on the normal direction. So first of all, in order to use the curl noise 2D, you need one parameter. Could be a vector value. So I'm going to add this point position plus some time-based value. So let's say time multiplied by some time-related value. Time multiplier. So let's say this is around 0.3. Okay. And now this is still in 2D. If you try to apply this value to a normal direction of this geometry, what you get as a direction is, as you can see, is aligned on XY plane. So which is not along this surface. So what I'm going to do next is to change the orientation of each direction using the function called dihedral. Which I've also explained it when inside for the matrix episode. Okay, and since the normal direction of this line that we have just created using the curl noise is XY plane, right? So the perpendicular to that vector field is Z direction. So we can use the Z direction as the normal direction of this vector field. And by using a dihedral, we can orient the vector, or we can create a rotation matrix which goes from one of the normal direction to another normal direction. And this normal direction that I have retrieved is the direction of this pig head, the surface of this, the normal direction at the surface of this pig head. Okay. So now that we have just created the orientation matrix, we can now rotate the direction using this matrix and then apply this vector field to as a normal field, a normal vector of this pig head, and as a result all the vectors being aligned to the surface like this, and can be used as a vector field, which in order to move the point on top of this surface. Okay, and let's see if it's going to animate as well. And you can see that the vector field is moving, and if we change the time it will go faster. If you change the scale, the noise will be more randomish. Okay, let's keep this to around 1.5 and keep the time to around 0.3 for now. Now, what I'm going to do now is to create a points which we're going to move using this field. So I'm going to use a scatter node on top of this pig head surface. Could be any amounts of values, but let's try to create tons of points so that we can see the changes. The next thing I would like to do is to set some life value to each of the point, so that at some point the point will be deleted and the new point will be reborn at some random position of this pig head. The reason why I'm going to do that is because if you look at the field, you can see that some point might be stuck to a specific position, like these point or these point where the speed is really slow. When the speed becomes really slow, then the point might stuck into those positions. So I think it's a good idea to remove the point at some point and then reborn the point at some random position again to continuously create a point flow animation. Okay, so that's what I would like to do, and in order to do that, one of the idea we could do is to create a life attribute to each of the point to determine when the point should be deleted or die. Okay, so let's connect the point wrangle from the scatter point, and let's name this rand life. So each of the point I'm going to apply a different life value, because if you set the same life value, then all the points will disappear at the same time, which looks too artificial. So I at life, I'm going to create an attribute, integer attribute called life, and let's create a random value based on its point, maybe with some seed value if you need. Okay, and as a result, the value you get here is a flow value in between 0 to 1, so we need to multiply this by some maximum number of life in order to make it as an integer value. So let's set the range for this max life to around 100, like this. Then for the seed, just change to any value you want. And then finally I'm going to use floor to make it a integer from the flow value. Okay, now let's check this out. I'm going to open up the geometry spreadsheet for the point, and I see those life attributes being created and a random value is being applied for each point from 0 to 100. Okay, that's good. Now I am going to what I'm going to do now is to as an initial value, as an initial direction of the point where it should travel or where it should go. I'm going to copy or sample those vector field to each of the point as a direct guide direction. So in order to do that, the easiest way we could do, since the point is stuck on the point, is placed on the surface, and also the vector field is also placed on top of this surface at each point, we can just use the component called or node called ray. So I'm going to connect the points on the first input of the ray, and second input we're going to input the surface. Now we can then check this import attribute from hits and also change the method for the projection to minimum distance, and as a result you'll be able to copy the vector field, or you'll be able to sample the vector field from the point position on the surface. Okay, that looks good. And if you play it, you can see that even though you have a less number of vector field, by sampling the in-between position of these vector fields, you're creating a really smooth vector field like these. Okay, and we're going to use this vector field to move this point using the SOP Solver. Okay, that looks good. Now let's try to create a SOP Solver at this point. I'm going to connect this point, which has this directional value inside the first input of the SOP Solver. Then connect this vector field as a guide to the second input. And simply we're going to do the similar things that we're doing here with this node and this node inside the SOP Solver for every frame, so that we can update the vector field of each point in each frame and use that to move the point. Okay, now let's do that. First of all, I am going to create the point wrangle. Okay, and let's name this move. Now, simply what I'm going to do is to move this point to a normal direction of each of this point. Currently we have this normal direction attached to each of the points, so we can use this normal direction as the moving direction. And we can specify some speed, how much it should travel. So let's multiply a speed multiplier parameter. Let's set it really slow, like 0.05. Okay. Now, also what I'm going to do is to add the life value, increment the life value for each of the point, or maybe make it subtract by 1 for each frame. And when the life becomes 0, then you can delete the point. Okay, so let's see how we could do that. If the I life is equal to 0, then we can remove the current point like this. Okay, now next thing we could do is to use the one we did previously. After we have moved, we can use the ray node to project the moved point onto the surface again, which is coming from the second input, this one. And also we can copy the normal direction as well. So make this minimum distance, and then check this import attribute from hits to copy the normal direction from the surface for the next movement. Now let's see what's going to happen here. I'm going to uncheck these and see if I play it. You can see that the point starts to move, and slowly all the points will be deleted based on its time life value. but seems like some of the point has not been deleted. Okay, some of the point is become negative. Okay, we might need to make this condition a bit more specific. If the life is less than 0, then we're going to delete it. Then that might work. Okay, and if we play it, all the points should be deleted at some point. Right. Now we have just deleted all the points, but after we have removed one point, then we want to reinstantiate or reborn a new point at some random position so that the total number of the point never changes as 10,000 for this exercise. So to do that, we're going to do the recreation of the points inside this movement. Right after we have moved, or right before we have going to remove the points, we're going to add a new point. So let's try to create that. And the point that we're going to create should be on top of the surface as initial position. So in order to do that, what we can do is to use a UV sample function to sample the UV value which is applied into this geometry. Now, fortunately, this pighead value or pighead surface has its UV value in the vertex, so we can use this for the UV sampling function to sample the position based on the UV. Okay, so in order to do that, we need to connect this second input guide geometry to the second input of this move component, and then we can sample the new position. Or before doing that, we need to create a random UV positions using random. So I'm gonna name this RUV rand at P. So this is going to be the random UV value, although the Z value is not going to be used for this one. And then I'm going to sample the position from the input geometry or second geometry using UV sample from the second input. What we're going to retrieve is point position, but as a guide, we're going to use UV, and we're going to use this random UV to sample the random position on the surface. Now, we can create a new point at the position that we have just found out. Then let's see how it's gonna look like. Okay, now if I play it, now seems like the new point has been created, but seems like the point is not really moving. So let's see where is the problem. Okay, then if you look at the geometry spreadsheet, the problem here is that the newly created points have the life equal to 0. So as soon as the point's been created, it's just going to die in the next frame because the life is 0. So we have to apply a new life as well for new created points. So I'm gonna copy the code right here that I have set the random life value right here inside the move node like this. So first of all, I'm going to create a integer life like this, and then use the set point attrib to apply the life to the new point with this life value. Let's also apply a new sliders here and change the seed. Okay, now let's see what's going to happen if I play it. Okay, so as soon as the point's been removed, the new point's being instantiated at some position, and we'll be able to create more continuously flowing point animation on top of the surface like this. Okay, which looks good. Now to make this flow a bit more interesting, let's try to visualize each of the point using the direction where the point is moving to, as well as the number of close nearby neighbors, and to use it for the coloring. Okay, so first of all, I'm going to count up how many neighbors are there to each of the point at specific radius. So I'm going to use the point wrangle. Okay, and let's name this and count. Now, first of all, I'm going to retrieve all the new points list using the function called near points at a current point position with some radius value. Okay, so for the radius value, let's say 0.3 or something. And I'm going to create a attribute value called count, which is going to be the length of this near points array. Okay, as a result, you'll be able to create a count value here, which shows the number of nearby points from each of the point. Maybe 0.3 was too big. We could reduce this to 0.2 or something. Right, now what I'm going to do next is to retrieve the maximum value of these count by using the attribute promote. So we're going to get the maximum value of the count from the point, and let's set it to detail as a maximum and don't delete the original. And let's change then the value name to total count. And as a result, you'll be able to get the maximum number of the neighbor points. Okay, now I'm going to use those information to color the geometry or each point using the color node. Let's set the ram from attribute and use the attribute called count. The maximum here is going to be the detail attribute, which you can access using expression using OP input. The name of the attribute is total count 0. So the range becomes 0 to 7 to 1. Now we can change the gradient to change the color map. So let's see, we can start from the blue. Then let's change the final one to yellow. And then maybe in between we can have like red and magenta. Okay. If we play it. Okay, now it seems like doing this coloring process is pretty slow outside the SOP Solver. So let's try to change this, bring this inside the SOP Solver and see if we can speed up this a little bit. Okay, I've just copied the things here, all the set here to color inside the SOP Solver, and go back and play it. Okay, I think now it's running fine. I think it was due to my CPU high load. Right now it's running on real time. So I think it doesn't really matter if you place this coloring code inside a SOP Solver or outside. Now let me also create a line out of this point and finish this exercise. So I'm going to create a point wrangle right after the SOP Solver. Let's name this flow line. And since each of the point has its normal direction or normal vector right here, we can use this to visualize the direction of the point as a line. So let's try to do that, which will create a bit more interesting animation, I think. So let's first create a new point which you want to connect with the current point. So add point starting from the current point position minus a normal direction plus multiplying some lengths of the line. And let's create a line using add prim with the polyline option between the current point number and the PT that I've just created. And let's also set the color to the same color that each of the point has to the new point. So set point attrib 0 CT PT with the current color value. Now let's promote the lengths and set the lengths for this for each of the particle. All right, now let's try to animate this and we'll create this things looks more interesting, which shows the flow, the direction where the point is moving to on top of the surface. Okay, seemed to work pretty fine. Now I think it still works even if you increase the number of points to 20,000. Yeah, looks great. But I'm just gonna keep it as 10,000. Okay, for the next exercise, previously we were using the geometry, the polygon as a guide object for the SOP solver, but for the next one I'm going to use the volume as the guide object for the SOP solver. Basically the idea is pretty much the same with the polygon for the volumes, but let's see how we could actually do it in practice. Okay, so first of all I'm going to create a box, and from this box I'm going to create a volume. Okay, and let's name this a vector value and name this velocity. Since I'm gonna use this as a a flow guide again, like we did for the geometry, like a polygon, but in this case we can create a three-dimensional noise value here, flow value here, instead of the 2D. Okay, since you have more space. If you show it up, it looks like these. Okay, now we can also raise up the resolution of the volume, like something to 50 by changing this uniform sampling diffs. Now let's try to create a three-dimensional flow inside this volume by changing each of the voxels velocity value. So I'm going to use the volume wrangle first, and then change the name to volume flow. Okay, now first of all let's create a vector flow value, which can be derived from the current point position multiplied by size. Now the point position is vector 3, but you can just convert it into vector 4. The last value, the W value, will become 0 in this case. The reason why I made the vector 4 value is because I wanted to change the last value based on the time, so that we can create a animation. So I'm going to use the time global attributes together by multiplying the speed to control how much it should run. Okay, let's change those values here. Now let me change the scale value or size value to something in between 0 to 3. Okay, Let's see. Now, now that we have created the position value which can be used for the seed, for the noise value, I'm going to create a directional vector using curl noise. In this case, it's going to be 3D using position as a seed. Okay, now I am going to apply or update each of the voxels velocity value with this direction. Okay, and let's check if the velocity, the name of the vector is velocity. Okay, now we can we do see some changes here, but we don't know what's the direction of each of the voxels. So to check, we can use the volume trail node to check the flow. Where does each of the volume or voxels is heading to as a volume, as a velocity. So I also need a scatter node to create a bunch of points inside this volume. So let's create such as like 3000 or 4000. Okay, and connect this to the first input of the volume trail, and second input I'm going to connect the volume like this. Okay, now it looks good, I think, and if I play it, the volume is also animated, and you can see the difference by changing those scale value. Okay, and also the time, make it faster. Okay, let's try to go with somewhere around here. Right. now that we have the guided animated volume and also the points that we can use to move using those volume. Let's try to create a SOP solver again. So SOP solver, solver, and first of all connect the points to the first input, and second I'm going to connect this volume. And what I'm going to do here is to move those points based on the volume's velocity inside the SOP solver. Now double click to go inside, and I'm going to use a point wrangle. Now connect the previous flame to the first input of the point wrangle, and the volume comes from the second input. So input 2 goes to the second input of the point wrangle. And let's name this move again. Okay, now first thing to do is to sample a direction for each of the point from the volume. So using the point position for each of the point, I am going to retrieve the closest velocity value or sampled volume value out of this voxel, the second input. Okay, so to do that, we can first name the velocity value as direction, and then use the function called volume sample v. If we are retrieving the velocity value, we use v. If not, if it's scalar value, then use without the v. In this case, we are sampling the velocity value, so use v, volume sample v, and from the second input, the name of the volume is velocity, and using @p, which is the point position, to sample the direction. Now we can increment, or we can move the point position using this directional value, maybe multiply by some speed parameter as well. Let's change the speed value to a slow value like 0.02. Okay, now I could also say volume velocity is, or I'll just keep it as it is. Okay, now let's see what's going to happen here. If I play it, you can see that the point is moving along the velocity, and when it goes outside the volume, it just stops because there's no more volumes available anymore. So what I would like to do here is right after the point has been going outside the volume, or the speed of the points become really slow, then delete that, or just move the point to some random position inside the box again. So let's try to do that. In this case, I might not need to delete the points, but just changing the position might be okay. So let's see. To check whether the point becomes slow or stopped, we can check the size of this directional value here. If this directional value, which has been retrieved from the volume, the size of this velocity becomes close to 0, then we can say that this has been stopped. So we can reinstantiate the position of the point somewhere in the center of this box. Then the point can find the volume from can find the velocity from the volume again. So let's create a conditions. If the length of the direction, which determines the speed of the velocity, is pretty small, like 0.01, then first of all, let's create a random positions in vector using rand, and this will create a vector random value for x, y, and z in range of between 0 to 1. So, but the the range of this box for x, y, z is in between -0.5 to 0.5. So what I'm going to do is to subtract this random value by set 0 0.0, 0 0.0, and 0 I mean 0.5 for x, y, and z. We'll create a range between -0.5 to 0.5 for all the coordinate. Now I can update the position using this random positions. Okay, now let's see what's going to happen. And as soon as the point has been stopped, it's going to be reinstantiated somewhere inside the box and random positions, and so that you can continuously create this kind of flow. Okay, that looks good. Now I'm going to do the similar things that I did for the pig head that I did here. So I'm going to first copy this flow line and show up the velocity here, although I think I need to change this so that currently the point doesn't have any directional value. So let's create that somewhere around here. So what I'm going to do is to create a normal direction for each of the point using this direction. Okay. Now I am going to set some lengths here, and if I play it, now you can see the flow like this. Now it might be interesting to set the color as well, so I'm going to go back to the previous exercise and copy all these, and this time maybe try to do this outside the SOP Solver. It should do the same thing. It's not a problem to have this outside the SOP Solver. That is because we are not using this updated color value inside the SOP Solver as a feedback value. So it doesn't matter if you do it inside or outside. Okay, so as a result, you get something like this. Looks pretty good. All right, and if you increase the number of points to like 10,000, still works just fine. Okay, so that's the example for the volume. Pretty close to what you did for the polygon. You just need to use a volume wrangle instead. Until now, we were dealing with the movement of the point using the SOP Solver. Now, the next things that I would like to show you is an example how you can modify the geometry using a SOP Solver. Specifically, I would like to show you how you can create a sculptural-like trail on top of a given geometry. You're still going to modify the point, actually, but the point are being used to create the primitives, and those primitives will be modified by changing the point position. Okay, so let's see how we can do that. First of all, I'm going to create a sphere geometry, which I'm going to modify it. And let's try to change this to polygon and set the frequency to something like 10. Or more is fine, I think. Now, after you have created the sphere, what I'm going to do next is to create a solver right away. Now, before get it inside the SOP Solver, what I would like to show you what I'm going to do here. What I'm going to do is to use a function called a sample sphere uniform to get the directional value or vector value, which can lead to a 360 degrees anywhere inside this, anywhere from center to anywhere, any position on top of the sphere, using a parameter, three parameters, x, y, and z. For the x and y, you can use it for the angle. For the z value, it's used for the scale. Okay, and let me just show you an example what it looks like. So I'm going to start by creating a single point. Okay, starting a single point, and I'm going to create a point wrangle on the next, let's see, line. And what I'm going to do here is to create a new line, a new point from this point position to a direction. Now this direction is the vector value which is going to be created by using a function called sample sphere uniform. Okay, and the parameter of this one is a vector value. So let's have x, y, and z for the parameter, like this. Okay, there might be too much parenthesis here. Okay, I think I need to close this one. Okay, still. Okay, has to be semicolon. All right, now I am going to change the z value, which indicates the size of the line here, with the size or the distance between the point to a new point. Now I'm gonna keep this z value to 1, and it might be easier to see the direction by connecting each of the point using a line. So I'd prim 0 polyline between the current point number and the PT. Okay, now the x and y value is used to determine the angle. First of all, x, okay, maybe starting from a y value, the y value can control the direction for the xz rotation, like this, for 180 degrees between 0 to 1. Now for the x value, you can use this to rotate using this z-axis for 360 degrees. So combining these x value from 0, 1 with this y value 0, 1, you'll be able to direct all possible direction. Okay. And by combining with the z value, you can also control the size as well. Now in this case, the sphere is set to a radius equal to 1, so I'm going to keep this value z equal to 1. But what I'm going to do is to change this x and y value iteratively to change the animation of the trail which runs on top of the sphere. Then I'm going to control that trail using a SOP Solver. Okay, so that's what I would like to do here. So by understanding how this sample sphere uniform works, let's go inside this solver and write some code to create a trail and use that trail to create some sculptural line on top of this sphere. Okay, so I'm going to first create a point wrangle and connect this one. Let's name this sculpt. Now for the sample uniform, I'm going to create a x and y value in order to change the angle. And for the x value, you can go from the value between 0 to 1 indicates the angle between 0 to 360 degrees. For the y value, it indicates the value in between 0 to 180 degrees. Okay, so by understanding that, we can create a kind of a looped animation or value for both x and y. For the x value, I'm going to create a variable like x. And for this one, I'm going to create a value based on the time. Maybe multiply by some speed value, speed multiplier. Let's set this to something like 0.2. Okay. And at some point, this speed value goes over 1. So as soon as it goes over 1, we can reset it to 0 by calculating the remains using the modulus. Since it's a 360 degrees, the range is 360 degrees, it's not a problem to set it 0 right after it becomes more than 1. Okay, so that's for the x, and for the y, it's in between 0 to 180 degrees. So for this one, we cannot do the same things like this one. If you do the same thing like this one, it just jumps the position or angle. So what I'm going to do here, in this case, if it's in between 0 to 180 degrees, I'm going to create a kind of a wavy animation. If it goes from 0 to 180 degrees, then goes back to 0 like a wave. And in that case, we can use a sine wave for that. So I'm going to use sine together with the time. Maybe use the same speed value to control the speed. Okay, now the sine value will create a value in between -1 to 1. So we can remap this value to 0 to 1. Okay. Now we are ready to use the sample vector uniform. So let's create a directional value, which is sample sphere uniform, and use x and y, and then the z for the 1 to set the size to equal to 1. Okay, now that we have got this direction can also be used as a position on top of the sphere, since the radius of the sphere is equal to 1 and the maximum size of this direction is also equal to 1. Okay, so this itself is a direction but can also be used as a position. Now what I want to do next is to use this directional value or position value on top of the sphere to search for the closest point on top of this from this base sphere. And specifically I'm going to calculate the distance between this value and each of the point position, and use that point distance to create a kind of a sculpted mountain. Okay, so float dist is a distance between the current point position to a direction, which can also be used as a point position. Now, I don't want to affect this distance value to every point on the sphere, but just a limited amount of limited search range. Let's also create a search range named as a radius or something. Okay, and let's change this radius value to something like 0.3. Okay, now what I'm going to do now is to limit this distance with this maximum radius size. So I'm going to use min distance between the radius. Now by doing this, the radius will become the maximum value and all the smaller value will be retrieved out of this distance. Now next I am going to remap this using the fit, which currently is in between the 0 to radius, but instead I'm going to change if the point on the sphere is close to this direction position, then make it 1. If it's far, if it's close to the radius or more than radius, then make it 0. I'm going to use this value to affect how much it should extrude it to the normal direction of the surface. Okay, so after I have done this, I can update the point position by moving it to the normal direction multiplied by this distance that I have just calculated, also multiplied by some moving distance for each step. Okay, spell mistake, has to be fit. Now we can change this value and see that there is a slight mountain change here. You can see slight changes here. They're currently affecting a single point here, also nearby points based on the radius attached here. Now by leaving the solver and play the animation, you can see that this extrusion is affecting the whole geometry and being animated like a trail. Okay, I might also need to attach the normal to make the normal being cleaned up right after you have modified the point height of this geometry. Okay, like this. So you can create this kind of geometrical modification, animated geometrical modification using SOP Solver, but as well, like this. Not just moving the point, but modifying the geometry would work. Okay, let's also increase the frame to see more. And let's try to change some parameters here, like changing the radius to a bit smaller value, and also move value to a bit smaller. Okay. So it seems to create a bit spiral trail top of this geometry, which is pretty interesting. Yeah. So this is one of the example you could use to to show how you can modify the geometry to show the possibilities. The next example I would like to show you is the basic fractal shape using a solver. A fractal shape can be created using the recursive method, which is same as the feedback loop that we've been using. And for example, for a simple example like L system, which is one of the fractal shape, you can start by creating a single line like this, and also determines the length, set the length and also the direction where it's going. Okay, now this is, consider this is the first frame, and on the second frame you can copy this line, copying this line from the first point to the end point like this. Okay, and what you can do next is to rotate this line by a specific angle for 2 times in different angle. So now you have 2 branch out of single line, having this angle right here. And you might also want to scale this one with the same ratio. You can either make it smaller or bigger. Okay, now right after you did this, on the next frame for this one, you can again rotate, copy this line and rotate like this, and keep doing this for each frame, and you'll be able to create a tree-like fractal shape, which is called as L system. So let's try to create this kind of fractal, basic fractal shape using a SOP solver, but also try to consider this grows as an animation, so that we would like to have a slowly animated growing trees starting from the single point, but slowly grows up until the first branch, then grows up in this direction and gradually grows like these. Okay, by using SOP solver it's possible to do this pretty easily, so I'm gonna show you how you can do that. Okay, so first of all, I am going to create a single point to start with, starting from the point at 0, 0, 0. And what I'm gonna do is to apply a initial attribute to this point, specifically a velocity value where this point should move on the next frame. So I am going to create a attribute create, and let's set the type to a point vector value, and let's name this val, and for the value I'm going to set it as 0.1. Okay, now same as I did for the this trail exercise, I'm going to attach a group so that only this grouped point will going to be affected by the code inside the SOP solver. So I'm going to change this point group and name this last, since the last point is the one that we want to move. Okay, now I am going to create a solver and start creating animation for the basic fractal. Okay, go inside. The first thing I'm going to do is pretty simple, like we were doing. I'm just going to move the point based on the velocity attribute which is attached onto the point. So I'm gonna name this move, and its name, let's retrieve the new point position by creating a new point position by getting the current point position plus the velocity. Okay, now I'm going to add a new point at this point position that I've just created. Previously, I was moving the last point, just by changing the at p value, but in this case, I'm going to use this updated point position for the new points, which you can do either way, but in this case, I'm going to do this way. Okay, and then I'm going to create a line between the previous points and the current and newly created points. Okay, so add prim 0 polyline in between the current point and the new point. Okay. Now, let's try to see what's going to happen by doing this. And also, I am going to filter this code by setting this group to last. So only the last group will be affected. Okay, and by doing this, I also need to reattach this last point group to the new point, which is going to be the lastly created point. So the lastly created point should have this last group, and the previous point should not have this last group. So I need to remove that from the previous one. So I need to do both of them in one code. So set point group for the last, and for the current point we can remove it, and for the new point we can attach it like this. Now we can set a new attribute to the new point, name as velocity. Okay, this should not be pt num, but this should be pt. And the new velocity can be derived from the current velocity, like this. Okay. Now let's go outside and see what it's going to do. If I play it, we'll just grow a bunch of line connection like these until infinitely. Okay. Now so far so good. Now the next thing I would like to do is to at some point, at some frame range, we want to have the branching using some rules, or maybe using some conditions. In this case, we could create a branch based on the frame. So let's try to do that. So going back to the SOP Solver, you can do in the same node, but I'm going to create another point wrangle to work with. Okay, now let's connect this one and let's change the name to branching. Okay, so first of all, what I would like to do is to set the condition when to create a branches. So I would like to create a branch based on the frame value. So let's create if conditions together with the frame and create the modulus remain calculation with some parameters. And if it's equal to 0, then do the branching. Let's promote the value here. Let's say around 20. So every 20 frames, the new branch will be created. Okay, now since I would like to create two splits, so the one branch becomes 2 at each 20 frames. So instead of using the same code twice, I'm going to use the for loop, starting with the -1, and then until +1, and I'm going to increment the I value by 2, so that you'll have 2 times loops by using this, starting from -1 and end at +1. And now I'm going to create a rotational matrix to rotate the direction. So starting frame ident, then rotate the matrix using a angle. Maybe that could be also parameterize, so let's say angle multiplied by pi multiplied by I, so that the one of the angle will be negative, one of the angle will be positive. Okay, and I would like to set the axis to 0, 0, 1 for now. Okay. Now that I have created the rotational matrix, I can now rotate the current velocity, which is attached to the last point by mat, multiply by mat to rotate the velocity. Now I also need to look for the last points as well. So only this function only works for the last branching point. Okay, now we can create a new line between, or maybe we could create a new point using this velocity as a new attribute value. So at point 0 at p plus velocity, and then create the line to connect between the previous point and the current point. Okay. Oops, not this, but polyline between the PT num and the PT. Now, same as what I did for the move, if I have created a new point, I should set a group called last, like this, and we also need to remove the point group from the previous one, like this. And we also need to set this velocity as a new attribute to this newly created point. So set point attrib 0 vel at pt num and pt as velocity. Okay. I think this one can go up outside the loop because we don't need to do this 2 times. Okay, I think this is all good. Now let's see what's going to happen around 20 frames, every 20 frames. So I'm going to go to the first frame and play it. Oops, nothing happens. Let's go and see what's going on here. Okay, I think I forgot to set the radius, the angle right here. So I forgot to promote this, so promote and change the angle to something like 0.2. Okay, now let's see what's going to happen. Okay, now at every 20 frame it will create a branches like this. Animated branch. Looks good. Okay, now it is placed on the flat XZ plane or XY plane here. That is because we are using the fixed rotational axis right here. Okay, so maybe by changing this value based on the frame value or something, might be able to create more animated or more twisted like angle with this one. Okay, so let's see how we can do that. We can probably change the X value and Y value based on the cosine and sine to change the angle, the axis circularly. So let's see, cosine and sine for the Z, and for the cosine value the radians, or maybe just based on the time, and also for the sine as well. And let's see how it goes. If I play it, now you can see the twisting happens at based on the time value or the frame value. creates more interesting three-dimensional fractal shape like this. Okay, that's really good. And you can modify all these parameters that I have set here, like the angle, step, or the when to create a branch. If I set it to 30 frames, the glows becomes a bit slower, I think. Like this. Well, what I wanted to show here is how you can simply create a fractal shape, and fractal shape basically is same as the feedback loop in terms of recursive calculations. So even if it sounds really hard to implement it, basically what you're doing here is pretty much the same as we were doing with all these previous exercises. Okay, so and probably using this group to filter which points should be activated or which point should be processed on the next frame is the important factor for this kind of fractal shape. Now the last example I would like to show you, or the last exercise I would like to show you, is the example for the chain solver. How you can use a multiple number of solver combined together or chained together. Meaning after you have done some simulations using a single solver, you want to use that result for another solver. You can do that by using a little bit of trick here. So let me show you how you can do this. So the example that I'm going to create here is the bouncing ball inside a bouncing ball. So first of all, I have this big bouncing ball which bounces inside a box. Bounced by the boundary of this box. And also this will be the single solver simulations. And inside this sphere, inside the ball, you have another multiple number of balls which bounces within this boundary together with looking for other balls as well, bouncing between the other balls as well. So that's what I would like to show you how you can do this, okay, using a SOP solver, chain SOP solver. So for these small one, there's another SOP solver, and for the big ball, there's another one big solver. So you have two different SOP solver being used together. Okay, so that's a bit more advanced topic, but let me show you as the last example. First of all, I'm going to create a first solver to bounce the ball inside a box. So I'm going to create a box now. Set the size as 1. Okay, and also let's set the normal for each faces using the primitive option. Okay, and I'm going to add a new point. On the center, starting from the center. And then I am going to set some initial attribute to this point, which indicates the direction where it should go. So I am going to create a point wrangle. Let's name this init bell. Okay, now I am going to first create a random vector value using a rand function, using some seed value. Since there's only 1 point that I'm moving, I can just create single seed value here. And then since it's in range between 0 to 1 for x, y, and z coordinate, I'm going to subtract all x, y, and z by 0.5 like this, and then set the normal direction of the point with the normalized velocity and multiply by some speed value to control how fast it should move. Okay, and let's set the speed to really slow, like 0.01. Right. Now, in terms of the initial setup, I think this is good. I am going to create a SOP Solver. Connect the point to the first input, and connect the box to the second input. Okay, let's go inside. Now, thing that I'm going to write inside the solver network is the bouncing function. So let's try to do that using point wrangle. So connect the preframe to the first input of the point wrangle, and from the second input I'm going to connect to the second input of the point wrangle, which is going to be the box geometry, which is going to be used to determine when the point should be bounced and to which direction. Okay, and let's name this bounce. Okay, now first of all, I'm going to move the point to the normal direction, which has attached to each of the point as an attribute. So if you look at this one, it just moved to one direction. Now the next thing I would like to do is to bounce this point right after it touches the face, one of the face of the box, and do the bouncing like this, like a reflection. Okay, so in order to do that, we need to determine whether the point is inside or outside the box. Okay, so one of the technique you can use to do is to use to calculate the dot product between the point position and the projected point on the box, and also the normal direction. So let me show you how does that work. So first of all, let's say we have this box like this, and say we have this point right here, somewhere in here, and one thing you could try is to first of all get the closest point for this point on this box surface, which is going to be somewhere around here. Okay, by getting the closest projected point, you also be able to get the direction from this point to the projected point position. Now you can also retrieve the normal value of this primitive which is at this point position, which belongs to this point position. So for the normal direction of this primitive is something like this. Okay, so this is n and this is direction. And now you can calculate the dot product between this one and this one. And if the dot product is, in this case, positive, then this indicates that the point is inside the box. Now if the point is outside the box like this, or somewhere around here, now the projected direction is something like this. And at this point, the normal direction of the primitive is this direction. And the dot product between the n and direction, in this case, is a negative, meaning what point is outside the box. So that's how you can determine whether the point is inside a primitive or inside a box or not, which works for any kind of geometry as well. Doesn't really have to be a box. Okay, so by understanding this concept, let's try to see if the point is inside a box or not first. Now to retrieve the closest point on a surface, there is a bunch of ways to do that. One way is to use the min-pos function, or one way is to use the xyz distance. Now an xyz distance gives you a additional output parameter like uv, which is pretty useful to retrieve the normal direction at the specific point position. So let's try to use that one. So first of all, I'm going to create a output parameter in order to use a XYZ distance. One is the primitive number and one is the UV value. And retrieve the closest distance between the point to the surface using XYZ dist from the second input from the current point position, and prim and UV will be feed as an output parameter. Now by using these values, you'll be able to get the projected point position as well as the project point normal direction. Okay, now let's retrieve the normal direction on the primitive at specific UV position. You can use that. You can do that by using prim UV function from the second input, a normal attribute, the prim UV. You can also retrieve the projected point position using the same prim UV function, but instead of using n, you can just say p, and all other the same parameter. Easy as that. Okay. As a result, you'll be able to retrieve the specific point position or specific normal values sample from this UV position. Okay, now we can calculate the direction between the position at projected point position minus at P, which is going to be the direction to the projected positions. Let's also normalize this. Now we can calculate the dot product between this direction and the normal on the surface. And if it's negative, then that means the point went outside. So that's when you want to activate the bouncing. Okay. So for the bouncing, what you can do is to first make the normal direction negative. But that's not enough, because if you just make the direction negative, like if the point is going this way, and if you make the normal direction negative, then just go to the opposite direction like this. But actually what we want to do is to make this point goes this way. Okay. So to do that, what we can do is to first create a opposite direction like this. That's fine. Now we can then use the normal surface direction, let's say Sn, and use this as a rotational axis to rotate this vector by 180 degrees. And as a result, you'll be able to bring this opposite direction to a reflected direction like this. So that's what I would like to do here as a code. So right after I have make it negative or opposite side direction, I'm going to create a rotational matrix. Matrix mat is equal to ident, and then rotate the matrix by pi, which is 180 degrees, using the norm, which is the surface normal, as a rotation axis, and multiply or apply this rotation matrix to the normal like this. Okay, and also since the point is currently outside the box, to make sure that the point is inside on the on every frame, I'm also going to change the point position so that it should always be inside a box. So what I could do is to first use the position, which is the projected position, which is this one, and add by the newly updated normal direction so that it goes inside the box just for little. amount of speed. Okay. And I think this should do the job, and let's see what's going to happen here. If I play it together with showing the box, as soon as it touches, it bounces, bounces, bounces around the box. Okay, looks good. Alright, so that's good. So the first solver is done. What I'm going to do is to create a sphere using this point as a center. So I am going to create a sphere node. Let's set this to polygon, set the frequency to 10 and the scale to 0.5. Okay, and I'm going to use copy 2 points. So that we have now a moving, bouncing ball like this. Okay, now what I want to do next is to use this bouncing ball as a new boundary for the points which should be play inside this ball. So to play the balls inside this boundary, we need to create another solver. Okay, so what we're going to do is to use the result of this solver as the input guide for the new solver. So that's the new stuff here. Okay, now let's go back to the previous frame, or the first frame, and I'm going to set up some geometry or for the points for the new solver now. Okay, now what I'm going to do is first I'm going to scale this sphere as a little bit smaller. So I say something like 0.75, 0.75, and use the ISO offset to make it as a volume, to convert this geometry to a volume, and set the uniform sampling diffs to something like 50, using scatter node to create a bunch of points inside a volume. Well, we don't want to have too much points because it's a bit hard to see if there's too much point for the bouncing, so I'm gonna keep this too small as possible, like 7. Okay, now we can set a initial value, initial velocity to each of the point, and probably the color value as well by using the point wrangle. Okay, and let's name this init points. Oops. Init points. Okay, now first of all I'm going to create a random velocity like we did for the first sphere. So rand at p plus some seed. Okay, and I'm going to subtract it by 0.5, 0.5, and 0.5 for the x, y, and z, and then apply this velocity as a normal. Maybe I should normalize this first, and then multiply by speed value. Okay, the speed, I think it's better that you make the speed faster than the previous bounding ball, which is specified right here. If this bouncing, the initial bouncing boundary of the sphere is faster than the sphere that I've created here, then you cannot really see the bouncing effect clearly. So the balls inside the bounce should have more faster speed than this one. Okay, so now currently I'm setting as 0.02 for these one. Okay, now Let's also set the radius of each of the point, set as a p-scale. Okay, so f at p-scale is equal to chf rad. And this p-scale is also going to be used to determine the collision between the points as well. Okay, so let's set it to point 1. Okay, around that. Now I think as initial value, initial setup, that is fine. So now I can create a new solver and connect this one to the first input and connect the one that I have got from the result of the solver to the second input. Now there's one thing you need to be careful when you change the solver. You cannot connect the result of the solver to the first input of the new solver, because the first input of the solver is only the first frame of the geometry is going to be retrieved from the pref frame. So even if you try to attach this to the first frame in first input, the only value you get is the first frame result of this solver out of the pref frame. You can still retrieve the animation value from the input 1 if you want to use that, but if you want to create the feedback loop based on the result of the animation, you shouldn't connect it to the first input, but rather connect to second to fourth and use it from these inputs. And currently that's what I'm doing here. I'm using the result of the first solver to the second input and use it as a guide geometry to use the result animation for the new simulation purposes. Okay. Now I think everything is set. So let's go inside and write up some code. Okay, now I'm going to create another point wrangle for each of the point, and the first thing I would like to do is to create a reflection or reflection functions for each of the point to interact with each of the points. So if this point and this point touches, then both of the points should go to the refracted direction, like this or like this. Okay, so that's what I would like to do here. So I'm gonna name this reflect. Okay, now to do that, first thing first, we can we could check the distance between each of the point. Okay. Now I can do that, and I would like to look for the minimum distance between those points and get the nearest point position from each of the point. Now I can do that by using a function called new points. If you just want to have a single nearest point, you might be able to just use this near point, but it will, since we are looking at the same input 0, which comes from here, there is a chance that this near point will give you the point itself as a closest point. So that's not what you want, but what you want is the second closest point, so maybe somewhere around here for this point. And this point, maybe something like this one. So to do that, the good idea is to use a new points instead of near point, and then set the maximum distance, which could be really high, but to set the maximum number of points you search to 2. So the most closest one will be yourself, the second closest will be the one that you really want to use. Okay. And we can check if the length of NPTS is really equal to 2. There could be a chance that it's equal to 1, which means you have only found yourself. If it's equal to 2, then you have found something close within this distance. Now if it's equal to 2, then you can retrieve the second index, which is equal to 1. That's the place, that's the position that you want to check. Now I can I can retrieve the point position at this point here. Now actually we could check if it's close enough or not by setting this value here as the radius. Okay, so maybe we could change this to p scale multiplied by 2. The p scale is the radius of single point, and if it's multiplied by 2, this will be the diameter of the sphere. Now if it's within this diameter, then the point is colliding. If it's more than 2.5, if it's more than 2.0, then you cannot find a point more than 2. So in that case, there's no collisions. But if within this p scale multiplied by 2, then the sum of the point is being collided. So that's when you want to calculate the reflection. Okay, now we can then calculate the direction where it from the current point position to the nearest point. So that could be npos minus current point position, and let's normalize this. Okay, now what we can do is to create a similar reflection or bouncing function that we did last time, using this direction as a normal the axis for the rotation. We could create a matrix starting with an ident and rotate this matrix by pi using this direction as an axis, then update the normal direction of the point by minus n by multiply by rotation matrix, and that is going to be the new direction for the point, the reflected direction. Okay, and we could also update the point position starting from the npos minus a direction multiplied by p scale so that the distance between the point and the closest point will have more than diameter of the sphere. Okay, and we could add a bn and the last to have a little bit of space between the points. Okay, now let's see if I play this. Okay, it's not moving. Okay, so we haven't moved the point yet, so we need to do that as well. So this is just a reflection, and we can move the point inside here. Point add by normal, like this. Okay, so at some point, some of the point has been reflected, if you could see. And it's a bit hard to see here because it's just a point. So I'm going to copy a sphere to each of the point. Since each of the point has a p-scale, the sphere size will automatically be set based on the p-scale. And let's slowly move this and see if the sphere is colliding or not. If you play it, you can see right here, the sphere has collided like this. So as soon as it touches, it has been reflected to go to the other direction. Now that looks good. Okay, now is the time to use this animated boundary as a geometry to collide with. Okay, where do this one? This animated boundary, I would like to use this animated boundary as a boundary of each of those points inside the space. So let's do that. I'm going to reset, go inside, and to do that I'm going to create another point wrangle, and let's call this move. And simply what I'm going to do here is pretty much the same as we did last time for the box. Okay, so I'm going to go back to the first solver and copy the code which I have written here. Okay, and let's go inside the solver and paste the one right here. Now there are some parts you need to change because currently we want to use the radius of the point so that we cannot check if the point has been touched to the bound, but we want to check if the outside surface of this sphere, which is using this point as a center, being touched to the boundary. So we need to consider that as additional parameter. So to do that, what we can do is to first of all change this one to so that it can consider the attribute, I mean the radius of the surface or radius of the small ball. So currently you have this big boundary for the sphere and we have this small sphere like this. Now previously we were just checking the point position whether the point is inside or outside to reflect the point. But in this case, even if the point is inside the sphere like this, but if we draw a sphere, the small sphere, then one of the some of the part is going outside the boundary, and that's not what we want. We want to reflect the ball as soon as one of the edge of the surface has been touched with the boundary. Then it should bounce. Now to determine if the point is inside or outside, considering the radius of the ball, then what you can do is to first retrieve the point position and do the projection to the surface. And what you can do is to move this point to the projected direction by a value of the radius. Okay, and if you move this point to the projected direction and by the radius, and if the point goes outside this big surface or boundary surface, then that means the edge is outside the sphere. And if you move the points to the projected surface, projected point direction, and by the radius, and it's still inside the sphere, then the surface is still not touching the boundary. So that's how you can determine if the ball has been touched with the boundary or not. And by understanding this, by getting this information, all the rest of the stuff is pretty much the same with the box bouncing previously we done. Okay, so what we need to do is to change this part, the direction here. Okay, so currently you are using the normalized position minus current position, but we need to update this position right here, which should be going from the current point position to the projected direction by a size of p scale, I mean the radius. Okay, so let's name this as projected point position is equal to current point position plus a normalized position minus current point position multiplied by p scale, and replace this with the position that I've just calculated right here. Okay, now it should search for the collision between the surface to surface. Okay, now after this, what you can do is to change this part. Currently this code, this line here is changing the point position sticking to the on top of the surface, but that's not really what you want. But you want to offset the point to by a p scale, the radius again. So you can do by changing this to position, the projected point position plus a direction multiply by a p scale plus p at n, and I think that's what you need to do. Okay, now let's see what's going to happen here. Let's show up the guide surface, guide boundary like this, and play it and see if the point is bouncing inside a big boundary, big sphere boundary, as well as reflecting between the small points or small spheres. Okay, and now it looks like it is working just as I want it to. That's good. Okay, now as a final touch up, I am going to merge the big boundary and the sphere all together, but in order to show up what's inside the big sphere, I'm going to set the alpha to this sphere. So alpha, I'll set the float alpha attribute, which you can control the transparency of the geometry. Now you can see like this. Okay, now you can merge these point geometry together like this. Now let's also colorize each of the point by random values. Going back to the init points, I'm going to set a color value by rand based on the point position, and then set the color based on the color attribute using the random from attribute using call. Probably I need to make the seed more bigger, so I'm going to multiply this by 1000. Okay, that looks good. Okay, now you see randomized colors balls running inside the big ball. Now, one more interesting you could try is as soon as those balls touch together, interacted together, you can change the color of these balls. So let's try to see that. Let's try to do that as well. So by going back to the reflect, so this is where it shows the contact between the two small balls. So right after it has find the contact, you can change the color to the random value again with some seed. And let's see what's gonna happen here. As soon as it touches, you can see, oops, maybe we need to go back and multiply this by 1000 as well. Okay, and play it. You can see that as soon as the ball touches with the other small balls, the color changes like this. Okay, and let's try to make the speed a little bit smaller for those small balls, like 1.5. Still works just fine. Okay, so that's how you can create a chained solver. One important things you need to remember is that when you want to use the result of the solver for the another solver, just connect to second, third, or fourth input, because you can only use it as a guide object. Okay, you cannot use it for the feedback. You cannot have the animated value as a feedback value, because the prep frame only can only retrieve the value updated from the last value, the last result of this movement or the solver's network. Okay, so that's one thing you need to remember. Okay, but understanding how this works, you'll be able to create any kind of simulations using a solver. Okay, so this is pretty powerful. Now this is it for the basics of solver. The one that I showed you is just the basics, how you can use the solver to create a simple simulations, to get used to using a solver for your purposes together with the VEX. Now I might gonna go back to a solver sometimes with a bit more advanced topics later. But for now, understanding all these stuff that I explained here is enough to start using a solver. Okay, and the next topic that I would like to talk about is half edge, which you might not use that much in usual cases, but in terms of computational geometry, in understanding how half edge works is pretty important. Especially if you want to do like a remeshing by yourself using scripting, knowing half edge, knowing how half edge works is essential. So I'm gonna show you the basics of half edge, what is it, and how you can use them for your practices. Okay, that's it for today. Thank you for watching, and if you like the video, please like and subscribe to the channel so that you can check out the new videos that I'm going to upload. And also I have started the Patreon page myself, so if you are kind enough to support me, you can go to the page from the video description of this video, and you can support me if you would find it helpful. Okay, that's it. Thank you very much, and see you next time.